Fair enough. All right, I'll make a quick intro first. This is probably a strange title, right? What does it mean? I don't know how many. Actually, how many of you are familiar with the concept of reproducible builds? Okay, excellent. So you're in the right place. The rest, you're also in the right place because you'll hopefully learn about it. Now, the idea here, we're going to briefly talk about a new idea of how to build a new Postgres distribution based on significantly different principles that other distributions are built as of today. Right? Just before getting into that, I'm going to hand back the microphone to my colleague again because he needs to introduce himself. So that was the reason.
I'm Javier. I'm just an infrastructure engineer. I've worked for a long time with hardware, distributed systems, and I don't know, like I came to this conference because of him. We've worked together for a long time, and I've used Postgres a while ago, and I'm using it now over the past year to build this hopefully awesome thing. So that's me.
Thank you. And well, myself, some of you know me already. I just try to do a lot of things related to R&D in Postgres. Most crazy stuff that gets crazy, but some stuff works at the end of the day. I also the founder of the company called OnGres, which means on Postgres. We've built open source software like Stackgres, which is a platform for running Postgres on Kubernetes. It's and well, yeah, that's it. Let's get started. That's enough about us, isn't it? So as I said, one of our goals today is to rethink Postgres distributions. And Postgres distributions, we know pretty much already, and we have packages and we have all that. So what is to rethink here? What is to reconsider? So let's think about a small hypothetical conversation, right? Like one of the reasons, or probably the most important reasons, or hopefully one of the most important reasons why you all use Postgres is because it's open source, right? And what it means is that, well, if you're running Postgres and something happens, you can always go back and look at the source code and understand what's going on. Or just because you trust it, because the source code is open and it's out there, you can just go and have some assurance of what you're running. But reality is that, unless I'm mistaken, you don't run source code, right? You run binaries. And those binaries need to be compiled and need to be linked against libraries. They're actually produced by someone. Unless you compile it and do it everything yourselves, most people are using packages, which are built again by someone. And there is a kind of problems that are lately surfacing a lot, called supply chain attacks, which is what happens when someone along the way is able to introduce some malicious software. That could be in the final binary. It could be as part of a dependency, which is exactly which happened with the famous XC problem, right? Security problem that actually Andres from here discovered, where deep into a dependency hierarchy of SSHD, there was introduced some malware that could be exploited to gain remote access to essentially any Unix server using SSHD, right? And the reason why this happened is because someone was able to inject this malware into a particular version of a small library that many other software uses, XC library. So once you're provided a package that is supposed to come from a healthy open source repository, how do you know it is not tainted? How do you know nobody infected that with some malware? So this is what we want to think about. We want our software not only to be open source, but to be safe, to be secure, or at least to be able to understand and verify whether it's safe and secure or not. Like if I ask you right now, you're running Postgres, right? Is your Postgres infected by this malware? Tell me. It's not easy, right? So we want to be able to tell very easily whether that's the case or not. How can we achieve that? There's a concept, it's not new, that is called reproducible builds. And the concept of a reproducible build, it's a build that you can reproduce. I'm not telling you much so far, but if there would be a way, I mean, if you think about it, compilers, they should produce the same output given the same input. So if I'm able to control all the inputs, the outputs should remain the same. So a reproducible build is a build that if I run it sometime later, if I run it elsewhere, I still get the same result, the same binary, bit by bit, byte by byte. This is the concept of reproducible builds. So let's negate this. If I cannot reproduce a binary bit by bit, byte by byte, that means that the build is not reproducible. Well, there are some gotchas here, some caveats, right? Sometimes I may get a binary that is different from another binary. This is, by the way, how we compare binaries by running a digest over them, like the SHA-256, right? If the SHAs differ, then the binaries are not the same. Sometimes the content inside is strictly the same, but maybe, it was, actually, for example, if you use different versions of tar, like BSD tar and GNU tar, you'll get different tar files and different SHAs, even though the content is exactly the same. So in this case, we may say, oh, we don't care if the content is the same, but validating that the content is the same may not be trivial. Also, sometimes differences may be in other parts. But anyway, it is a good goal if we could produce reproducible builds all the time, because in this case, there is an assurance that there's always a mechanism which we can use to verify whether our software is infected or not, where is actually its provenance, where does it come from. So, if we don't have reproducible builds, first of all, we have what I was been saying so far, right? Little warranty of how the binary was built. I cannot reproduce it. Furthermore, how do you troubleshoot in dev testing environment, right? The ideal way of reproducing in a problem in a test development environment is that I get the same binary and test it in a different environment. But sometimes it's not even easy to get the same binary in both environments, right? And also provisioning is harder, because if I warranty that I always get a reproducible binary, I can just cache it and distribute it elsewhere. Otherwise, I need to keep versions and versions of different builds. Let's make it a little bit more complicated. Let's also look for hermetic builds. A hermetic build is a build that does not depend on the environment where it's being built. In other words, it is not poisoned by the environment. All the time, in a sense, when you're building something, your environment is affecting the build. Typically, there's a compiler in your environment. There's libSSL in your environment. There's glibc in your environment. There is plenty of stuff in your environment that it's going to end up being some part of the binary. So the build is not going to be hermetic. A goal is to try to look for hermetic builds, which are absolutely independent of the environment. In this case, if we combine both, we have really powerful things. We can achieve true reproducibility, because now any way of building a binary anywhere, at any time, on any environment, will lead to the same binary. Right? So I can really achieve reproducibility. Obviously, I can achieve protection from poisoning from the environment, because the environment does not affect the build. So even if you introduce a malware in the build environment, we'll be safe from that. It will not matter. Right? And if Postgres could be compiled statically, which cannot, right? But it would allow the option to generate also a static binary that is built in a hermetic way. So a really powerful mechanism. Now, I'm not going to get into all the details about how you can break hermeticity and or reproducibility. Essentially, it's things that get injected from the environment into the binaries. Could be things like timestamps, like the run path, the R path, the build ID, a lot of strings that sometimes it gets generated through, during code generation phases and end up being part of the binary. In Postgres, Flex does a lot of this job of adding things from the environment. Just do a strings on any binary from Postgres. You'll see paths from the path where it was being built. That's simple, right? Obviously, if you use different versions of dependencies, you'll get different versions, right? Now, you could say, but look, in Postgres, we have Debian. Debian is fully reproducible. That's what they claim. And they are essentially right. But there's a condition, and their predefined build path environment. So this means you can reproduce Debian packages as long as they compile it in the same host and under the same conditions that they build them. Which is kind of good, but I want to myself go on my laptop and verify a build. That is the way I can protect myself against supply chain attacks. right? So we want to achieve reproducibility in a commoditized way, like anyone could verify in a reproducible way in your own environment. So much that this is a screenshot from the Postgres wiki page that claims that Postgres source packages, not even the binaries, the source packages are produced in a host where only 2 or 3 people have access to warranty stability. So that means that none of us can produce the same source packages than Postgres can, unless you are one of these 2 or 3 users, which obviously has, you can imagine, many other, I mean, these 3 people are really fine people, right? But they are 3, and they can be subject to other, kind of attacks like human. So, we're trying to solve all this by creating a new project called Monorepo. Monorepo is a monorepo for Postgres. So what does it mean? The idea is to create the Postgres monorepo. A monorepo is the place where everything is self-contained. In other words, in this case, Postgres and all the extensions. All in one place. One ring to bring them, sorry, yeah, you get the point, right? A place with Postgres and all the extensions where we can build them and package them there, right? So let's talk a little bit about this. And the goal is that this monorepo will become an upstream distribution, an Apache licensed, fully open sourced distribution where anyone can create a derived distribution to package in a certain way, to derive packages, to select which extensions you want to package, do whatever you want, and get your own distribution. Follow all these principles about reproducible hermetic builds and whatnot. It's technically both a binary and potentially even a source distribution because we are bundling somehow the source code into the monorepo. So now, this is work in progress. This is not theory. It's not finalized yet. But there is a lot of work being done here and a lot of results. I'm going to hand out to Javier to complete the picture.
Thanks. So how do we get there, right? So Monorepo aims to do all of this. It's basically cardinality problem, right? Like we need to generate a lot of stuff. We're aiming to support 5 major versions like Postgres does, with all the minor versions in between. Option sets is something that we think will be useful because not everybody needs all of the compile time options available, compile at once basically. And we also want all the extensions, all of them ideally. And that's a lot. That's as it was presented in other conference, in other talks in the extension day, like somebody has compiled like a 1,000 plus list of them. So it's a lot. We don't know if we will get all of them, but at least we'll try. And we want to compile them for now, for all major and minor, to avoid ABI problems like 17.1 had. So this takes us to, like a pretty big number. That basically means we're going to have to produce more than 1 million packages, 1 million compilations, right? And when you need to compile so much, you can do it on a laptop these days, but it's going to take a very long time. So we went out and started looking for how to solve this, how to do this. And the very first thing that comes to mind, right, is, well, we'll just wipe some Python scripts. I'm just going to generate lots of Mason calls, right? And compile Postgres through Mason or through through configure make. And that's basically what we've done, but better. Because we're using something called Bazel. And Bazel is a very mature open source build framework, build system. Open sourced by Google from their internal Blaze, which was actually an evolution of Makefiles and Python and what I just described. So it's very fitting. Why did we eventually choose to do it on Bazel? We've tried a few things first, but we found out that it has support for remote builds. And when you're targeting, as I said, huge number of builds, you don't want to do it on your laptop. You want to do it somewhere else, on a build farm. And we don't like to reinvent the wheel, so we just went out looking for who does this at scale, and Bazel and many others do this. Bazel has basically become the de facto standard for a protocol to do these remote builds. Everybody is jumping along. Back is Facebook's build system. Buildstream, Pants, everybody is eventually converging. Whenever somebody wants to do remote builds, they converge on this because it's a gRPC protocol, it's open, it's pretty simple. There's industry support, which for us was also important because we didn't want to have to like go and first build a build farm. We just wanted to try it out. And you can actually just run with one of these vendors. And you don't get locked in because it is open and there's open source that you can build yourself later on. So, you know, seems pretty nice and pretty good. On top of this, Bazel is pretty extensible and it's polyglot. It basically allows you through a very high-level language, which is an evolution of Python. It's a Starlark. It's just Python that is deterministic and hermetic. So it simply allows you to just write scripts, those Python scripts that I mentioned, but better. And it's polyglot, which basically means that there's lots of features that allows you to build other languages, not just C or not just one language. Which becomes handy because apparently there's a lot of extensions out there and a lot of people write them in C and in Java and in what else, I don't know, like in Rust, actually, yeah, true. So lots of them. Going full circle, it also so happens that basically that Bazel cares a lot about hermeticity and to achieve that, it provides sandboxing by default. So it does construct all by itself a separate directory called the exec root, where it basically puts all the inputs and it produces all the outputs, isolated from the environment. It uses operating system mechanisms like containers or a sandbox mechanism in Mac to prevent leaking to the outside world and vice versa. So it's isolated. And this is also pretty good when you want to end up having a reproducible build, right? And it's pretty massive. 10 years, open source 10 years ago, has a huge community and lots of third-party extensions that end up making your life easier. Because, again, we don't want to reinvent the wheel. We can write a lot of software, but if you can already leverage a hell of a lot of software from them, much better. The community writes lots of what's called rules, which are like packages of software that does certain things. Rules PKG for packaging, so you can package in tar, zip, deb, or RPM if you want. Rules OCI to build OCI images, and there's a lot of very easy discoverability because there's a central registry where you can just browse and look if somebody has written some piece of code that you actually want and need. But it does have pain points. The first one, not even listed there, it's a complex system and it takes a while to learn, like everything else. But again, like everything else, has trade-offs, right? It's very abstracted, so you have lots of layers in direction. That's good when you want to build a complex system like we want to do. And the cost is basically understanding it and debugging it because of the layers, right? The hermeticity and reproducibility aspects, it does hermetic builds, it does sandboxing, but that abstraction actually brings you into more complex debugging, right? And the debuggability, the UX of that is not that great. And in the end, basically ends up not forcing you, but the easiest path to have like a very nice, easy sandbox is to build a container image, which in itself is sometimes hard to build reproducibly, which is a big contradiction, but we've managed. Now, little quick code tour, because this is still not open sourced. It will be soon, but at least you get an idea of what it takes. This is it. It's pretty simple, right? So to build all of the Postgres versions, you can see there's two loads. The first one is the config. The second one is a macro. So you call a macro with a name and a config. What is a config? This is it. So basically a config is just the versions, the option sets, the repo name, right? We're calling new, like imagine an object, right? And what it does is nested for loops, because again, this is cardinality. We're just building the Cartesian product of all of these combinations, and we're putting all of this data into an object, just a struct called a target. This is gonna feed into the actual macro, which is the pg build all, which again is just a for loop. It's Python script, right? This is Starlark. It's syntactically identical to Python for most of it. And the PG build is the actual meat. This is the actual place where we end up calling Mason. And that's almost about it. You call Mason with all of those arguments, which is literally the exact same thing that you do when you build it. The only thing is, if you see the input there has a PG source, right? So we've built another little abstraction in Bazel called a repo, which basically is grabbing the source code for Postgres and making it available inside. And all it takes is some code that we've written. This download archives is a helper that we wrote. But then this is it. It's just a JSON file. So by adding to the JSON the file with the digest to be verified, like Alvaro was saying, you want to make sure that you're actually running, you're compiling what you actually want to compile and not something else. You can actually just keep adding versions and it will keep building them. It's that simple. So quickly, what's next? And I'll hand it to Alvaro to finish.
All right. So, well, first of all, this is going to be open source in the next few weeks, and yeah, well, it's a fully Apache 2 licensed project. Then we are already working in what we call Monobot, which is a crawler that actually is trying to reach repositories with existing Postgres extensions, and then inferring some metadata from these extensions and generating that repo.json file that he just shown before, which is the one that uses the build system to build extensions. So in other words, we're going to be able to fully automate building every version of every extension and for every Postgres minor version on every architecture, like on every compilation set, like everything that we just mentioned, fully automated, in a fully automated way. Obviously, we want to add more extensions. Right now, we just have a few. We're testing with some samples, but with this metabot also, sorry, the monobot will be able to fetch this, reach this goal of hundreds of extensions and all purely automated, reproducible builds, right?
I'm pretty sure we can build almost all of PGXS extensions. So, even if they're not in the repo yet, they should be. So,
yeah.
Metabot will do that.
We also want to provide support for multiple glibc versions because that creates a lot of issues and a lot of pain for a lot of people. If you just realize we're not talking about the system packages, this is Debian, Red Hat, this is distribution as agnostic, this is distroless. We want to generate packages that can run anywhere. And so we will build against multiple glibc versions. And last but not least, we want to also support forks or Postgres development branches, as they are called somewhere, like Babel Fees, Ivory, you name it. So that's it. Time for questions. Sorry, can you repeat?
What does the committee think about it? Like, so about you putting this out in the
The committee?
Yeah, Postgres committee.
Postgres committee about the logo?
Yeah.
I don't know. Didn't ask. Actually, this is the first time we talk publicly about this. The logo is actually, well, actually you can explain how the logo is generated. It's quite a nice story.
No, I mean, it's just an SVG file. I didn't get the question.
What does the Postgres committee think about you releasing this in the fashion you are?
What?
No comment. I wouldn't expect there was.
Yeah, I mean, that's like, I didn't, anyway, yeah, like, there's no conflict, like, there's no.
I wouldn't expect there necessarily was.
So I'm now dealing with ODBC, and we need to produce an ODBC driver on ARM for Windows.
Nice. Yeah. I mean, I'm sure, like, it would definitely help to build it with something like Bazel, for sure.
Actually, for you, Dave, only, well, everybody, but Bazel is written in Java. The configuration language is Starlark, which is a derivative of Python, but the engine, Bazel, is written in Java. And it's also it's used for building packages in many languages, but it's definitely used a lot for Java. And the guys who are in Java here, we don't know each other. We can talk about that. It's hard, takes some time, but it's great.
But you didn't see any Java here, right? Yeah, it's already, it's AMD 64 and ARM 64, so yeah. Well, I mean, for now it's only Linux, but yeah, like it's just adding yet another, and that's where the build farm comes very useful, and it's totally supported. Like Bazel builds on Windows and everything, so.
You use a smaller font.
Yeah.
Fair enough.
So does the Bazel abstract all the like the configured, does the timestamp information about like the build host? It just makes it deterministic so that.
So that depends on the actual source you build. If the source is not properly written, like if you call rand in your source, then for sure it's not going to be reproducible. So it's a two-way job. Like it does block I/O, and it does the language being deterministic. So you first configure it, and the input is deterministic. So at actual compile time, because of the sandbox and the way everything is written, you don't get to have that type of access. But if your code calls time or reads a file that has a timestamp or uses the path or whatever, then you have problems. Exactly. And that's basically what also happens with Postgres and what we are cleaning.